In this last unit video for Unit 2, we're going to look at graphing inequalities and absolute value equations and inequalities. We want you to be able to graph two variable inequalities and also graph absolute value equations that have inequalities as part of it. All right, so the first part here, you have to do a little remembering of what we did with inequalities before. Anytime you have a less than or greater than sign, we always want to use a dashed or dotted line with those. Okay, anytime you got the or equals to with it, then you want to use a solid line. Okay, so your boundary line, the line that kind of determines if those points are actually part of your graph or not. If it's dotted, it doesn't mean it is. If it's solid, it means those points actually on the line are answers themselves. So let's take a look at one of these. We are going to try to graph this one, 2x plus 3y is greater than 6. We want to graph this out. Now, one thing we can do to help us is identify, okay, any intercepts, okay? And you can do that by that cover-up method that we've talked about before. So if you were to cover up the y, okay, which means basically putting 0 in for y, what do you get when you solve the rest of it? Well, you got 2x is greater than 6. If you divide by 2, it means x has to be greater than 3. Or really what we're looking at here is not so much the greater than part with this, is that x is going to equal 3. That's where the line is going to pass through the x-axis at 3. Okay, if we do something similar by covering up the 2x or putting 0 in for x, I got 3y equals 6, and y would be 2. So the y-intercept on that one is 2. If we were to connect these now, that would give us our line. Okay, so if we go ahead and connect those, you got the equation of the line here. Looks something like that, and that's the line that we want for this one. Okay, so that's one way to do it. Another way you could do this would be to solve it for slope-intercept form, and we've done that too. If you solve this for slope-intercept form, first thing you'd want to do is try to get this y by itself. So start by subtracting 2x from both sides. That cancels out. Okay, next we got to get rid of the 3, so divide everything by 3. Okay, that cancels, so we just got plain old y here. We're dividing by a positive, so we don't need to switch the sign. And since 3 doesn't go into 2, let's just leave that one as a fraction. That's going to be our slope, and then 6 divided by 3 is 2. So this should be the equation of that line, and it should give us the same thing. Here the y-intercept is 2. Okay, that's what we got here. Our slope is right here, negative 2 over 3. That means down 2, right 3. We should get the same thing. If we go down 2, right 3, down 2, right 3, we get the same thing. Or we could go up 2 and left 3 from our starting spot. Either way, it gives us the same exact line. So that's part of what we need to do here. And the reason we chose dotted line again is because of the symbol we got here. Okay, to start with, our symbol did not have the equals to. Now you have to do some shading. Okay, and the reason we shade is that so far on this graph, we don't have any answers. Even the line itself is not an answer because that's where it would be equal to that, and we're not equal to it. So to figure out which side to shade, you are going to test a point. Okay, and the way you test the point is by picking a point that we could use here to test to see whether this comes out to be true or not. So an easy point to test is the point 0, 0, the origin, right there. Okay, 0, 0 is easy because when you multiply with 0, it makes everything come out really easy because anything times 0 is 0. So what we're going to do here is test 0, 0 by putting 0 in for x and 0 in for y. And again, the reason 0 is nice is anything times 0 is 0. 3 times 0, that's 0. 0 plus 0 is 0. Is 0 greater than 6? Well, that statement is false. Okay, 0 is not greater than 6, which means 0, 0, the point we just tested, is not a solution. That means if I picked any points on this side of the line, no matter where I picked it, none of these points, if we tested them, would make this statement over here come out to be true. All the points that do make it true are on the opposite side of the line. So what you want to do then is on the opposite side, you want to go ahead and shade that in. The shading indicates all your answers are on that side of the line. Just to show you that it does indeed work, the point's on that side. Let's pick a point on the shaded side and try that. Like here's the point 2, 2. 2, 2, if we put that point into this problem, should make this come out to be true. So let's test 2, 2 instead. So if we go 2 times 2 plus 3 times 2, 2 times 2 is 4, 6, 2 times 3 is 6. If we add that together, we get 10. Is 10 greater than 6? Yes, that's true, like it should have came out to be, because all these points on this side make it true. So you want to shade then everything on that side. All right. Let's try another one. Number 2. We want to do the same thing on this one. Why don't you pause the video, try this one on your own first, and then see how it goes here in a second. All right, let's see how you did. One way you could do is to find the intercepts. If you do that cover-up method, okay, you got negative x equals 4. If you divide by that, looks like the x-intercept is negative 4. Okay, if you did the same thing, cover up the y, or sorry, cover up the x and solve for the y, you got 2y equals 4. So then the y-intercept is 2. That would be here. So one way to do it would be to connect those to get the line. Another option would be to get it in slope-intercept form. Maybe some of you did it that way if you add x to both sides. Now you got 2y is greater than x plus 4. We could divide by 2. Divide everything by 2 there. That cancels. We're dividing by a positive. We don't need to flip the sign. 4 divided by 2 is going to be 2. This one's a little tricky because there's no number in front of that x. We know it's a 1 though. So that's like 1/2 x. So you could also graph it this way. Y-intercept would be 2. That's what we already got with this dot right here. Slope is 1/2. Up 1 over 2. Up 1 over 2. Or down 1, left 2. Down 1, left 2. And notice it goes through the same point right here. Now connect them. What type of line should we use? This is telling us dotted. It doesn't have that or equals to. So connect them with the dotted line. Lines, points on that line are not solutions. Okay, now the last thing, we got to shade. Don't forget to pick a point and test it here. Which side should we shade on? Pick a test point. My suggestion, use 0, 0. The only time you can't use 0, 0 is if the line actually goes through that point. Our line doesn't go through that point, so we can use 0, 0 to test. So if we test that, that's all going to end up equaling 0. Is 0 greater than 4? No, that's false, which means 0, 0 doesn't work. No points on this side work, which means all the points on this side do. Should have had the top left-hand side shaded. All right, some other stuff you should be able to do with inequalities. If you're given a word problem or a situation, you should be able to use inequalities with that too. This one says Manny has $15 to spend at the fair. It costs $5 for admission, 75 cents for each ride ticket, and 25 cents for each game ticket. Write an inequality for the number of ride and game tickets he can buy. Okay, so Manny's total here looks like 15. So he's got $15 to spend. Everything he spends it on better be less than or equal to that 15. Otherwise, Manny's going to be in trouble if he tries spending more than 15 and doesn't have that money with him. So what does he spend it on? Well, he spends $5 for admission. That's a one-time cost. He doesn't spend that more than once. 75 cents for each ride. So 75 cents times each ride. We don't know how many rides he's going on. Let's put R there for rides. plus he also spends 25 for each game ticket. We don't know how many game tickets he's doing. Well, let's use G for game tickets. So all this stuff he's spending on better be less than or equal to 15. Well, two of those parts, we don't know how many rides or games. We know for sure he's spending this $5. So since we already know he has to spend that, let's subtract that. We know for sure that's got to come off. So our equation here would be 0.75 R plus 25 cents for each game ticket. Better be less than the $10 he has left after going in to the things. So let's see if we can answer some questions now. If he buys 10 game tickets, how many ride tickets will he be able to buy? Easy. Now that we got this equation, it's 10 game tickets. Which variable should we put that in for? G. All you got to do is substitute it in and see what you get. So you got 0.75R plus 25 cents for those 10 game tickets. If we multiply that out, that means he's spending $2.50 on games. Subtract that from the $10 he has left. That means he's got $7.50 left. How many? Forgot the variable in there. How many rides can he go on then? Well, if we divide 750 by 0.75 or 75 cents, looks like we would get 10 or less. He can go on 10 or less rides. All right. What would be the maximum number of ride tickets he can buy? Well, the maximum number of ride tickets would mean if he wants to go on the most rides, we got to assume he's not doing any games. So if he's not doing any games, okay, we're basically taking that out of the equation. Okay, that would be like substituting 0 in for the games. So what would he get? That'd just be spending 75 cents for each ride, less than or equal to the $10 he has left. Divide that out, and that should be it. So if we divide by 0.75, how many can he go on? So it looks like the rides would have to be less than or equal to, let's divide that out and see, 10. Divided by 0.75. And it looks like you can go on, well, 13.3 rides. Well, obviously you can't go on 0.3 of a ride. I don't think they're going to let you do that. So probably the most rides looks like would be 13. Since you can't do 0.3 of a ride, 13 would be the most. Why don't you pause it, try the last one, see what's the most or maximum number of game tickets he can buy. All right, let's see how you did. Very similar. If we're not doing any, or we want to see the maximum amount of games, that means we're not doing any rides. So it'd be like putting 0 in there. So we know that 25 cents a game, $10 to spend. If you divide that, you should have gotten that. It has to be less than or equal to 40, which means the maximum he could do would be 40 games. All right, flip to the other side. The other thing we want you to be able to do is graph some of these absolute value graphs and absolute value inequalities. Yes, the last notes you watched, we looked at how to do these absolute value ones by making a little XY table. That will always work, okay? But there's another method you can use to help you, and that's looking at what these numbers do to the graph. These numbers right here move your graph from the original absolute value graph that we looked at. The original one, if you just graph absolute value of x, that's what the graph looks like. Its vertex, that's what we call this point, right here, that's the vertex, is at 0, 0, and it's just y equals absolute value of x. And the slope of both sides, the slope on this side is 1 over 1, or 1, and the slope of the other side is -1. Okay? These numbers, if you start adding other numbers in, added and subtracted inside that absolute value sign and outside the absolute value sign, shift the graph or slide the graph. You talked about translations in geometry. They slide or move it. anything outside the function, and the function here is absolute value, anything outside the function is going to move it up or down. It's going to be vertical. It's going to move it vertically. If it's plus, it's going to move it up. If it's minus, it's going to move it down, just like you would always do with plus and minus on a graph. So in this case, this plus 7 right here is going to shift the graph up 7 spots. Anything inside the function, like this plus 5, so when we're inside the function, or in this case inside the absolute value, that shifts it horizontally. Horizontally means left or right. Okay? When you're inside the function, though, it's always opposite of what would normally happen. Anything that happens inside the function, it's always opposite, which means usually plus 5 here would mean we're going to the right, because positive is usually to the right on a graph. But remember, we're opposite inside the function, so the plus 5 actually is going to move it left 5 spots. Okay, so inside the function, if you're adding something, it actually is going to go left. If you're subtracting something, it's going to go right. And so the vertex for this one would be at, instead of 0, 0, if we move 5 left, that's going to be at negative 5. If we move up 7, that's going to be at positive 7. So the vertex would be, instead of at 0, 0, be right over here. And we'd get the same slope on that side and that side. Okay, let's try one. See if we can use this new method to help us out. So we got this absolute value graph. What are these two things going to do to the graph? Well, the minus 2, that's outside. That's no, it'll do exactly what we think it would do. It's going to move it vertically, and minus is down, so that's going to move our graph down 2 spots. So if we're starting here, now it's here. Okay, now what's the plus 1 going to do to it? Well, that's inside the function. Inside's going to move it left or right. Inside the function's always opposite. Normally plus 1 would move it right, but since it's opposite, that's going to move it left 1. So now instead of at 0, 0, it's going to go down to left 1. This is going to now be the new position right there of the vertex. All right, now to get the rest of the graph, since we don't see anything else in front of that x, which we know there's a 1 there. If there's a 1 there, that means the slope is up 1 over 1 on the right side. And on the left side, it's going to be a slope of negative 1. So it's going to be that same V shape we've seen before. There's the graph of this one. If you made a XY table like we did before, you should get the exact same points as we got here. Just to show you it works. Watch if we put, say, negative 1 in there. If you put negative 1 in for x, negative 1 plus 1 is 0. Absolute value of 0 is 0. Minus 2 would be negative 2. We should see a point at negative 1, negative 2. Yep. What if we put, say, 0 in there? What if we put 0 in for x? Well, 0 plus 1 is 1. Absolute value of 1 is 1. 1 minus 2 is negative 3. It's 0, negative 3. Oh, sorry, not negative 3. 1 minus 2 would be negative 1. Is 0, negative 1 there? Yes. Okay, and it'll work for any points. You'll get the exact same points if you did a XY table. Let's try another one. Number 5. They want you to do this one. See if you can pause the video here and figure out what is that number doing to the graph? What's that number doing to the graph? And then see if you can sketch it out. All right, let's see what you got. Plus 1, that's outside. That's going to move it up 1. Minus 4, be careful on this one. It's going to move it left or right, but it's opposite. Negative actually is going to move it right 4 spots. So instead of at 0, 0, we want to move right 4, up 1. There's the new vertex. We don't see anything in front of the x, meaning there's a 1 there. So the slope on the right side is up 1 over 1. Slope on the other side is down 1, right 1. So the graph should look like that. It's that same V shape we've seen. All right, last one. Okay, same thing on this. Here, minus 3. What's the minus 3 going to do to it? That's going to move it down, down 3. We don't see any numbers being added, subtracted on the inside, so it's not going to move left or right on this one. Okay, no movement left or right. Okay, so it's not shifted left or right at all. There is that 2 there. We'll talk about that 2 in a second. So this one, instead of at 0, 0, just goes down 3. All right, now what does that 2 do to it? Well, normally on the other ones we've been going, it's up 1 over 1. Not here, though. This one has a different slope. This one has a 2. So this 2 is indicating your slope here. Our slope is going to be 2 or 2 over 1. That means go up 2 over 1, up 2 over 1, up 2 over 1. Okay, and on the other side it would be up 2 left 1. So it looks something like that. Okay, now we want to connect these. Now, on the other graphs, we just connected them, we were done. This one a little bit different though. We got an inequality here. Okay, so now you got to go back to the inequality stuff. Solid or dotted line? Well, since it doesn't have the or equals to stuff, we want to use a dotted or dashed line on this one, on both sides. Okay. Also, can't forget, we got to be doing some shading here. Okay, so to shade, we want to test the point again. And our easy test point again, 0, 0. 0, 0 is always going to be easy. Only time you can't use 0, 0 is if our line goes through it. Our line does not go through the middle there. So let's test 0, 0. What if we put 0 in for both x and y here? What's that going to do to it? Well, we put 0 here. That's just 0. On this side, put 0 there. Absolute value of 0 is 0. 0 times 2 is 0. So that's 0 minus 3. 0 minus 3 is negative 3. Is 0 bigger than a negative number? In this case, negative 3. Yeah, if you think about a number line, 0 is bigger than a negative. Anything to the right is bigger. 0 is bigger than every negative. This is true. If it comes out true, that means you want to shade everything on the side where 0, 0 is, because anything we pick in here should make this one true. So now you want to shade everything inside of this absolute value. And that's what the graph looks like. All right, you try some of these out on your own now on the practice.